Good morning. I'd like to speak to you just in general about the history of recycling of carbon fiber composites. It's not new. Doesn't want to play. Go back. Right. That way, so it goes that way. All right, so we'll go through a bit of history, a bit of the whys and wherefores of reclaiming and recycling carbon fiber, a system that we are currently developing that gives a third string to the bow in terms of all the policies that we have for recycling. And a case study that we carried out just to see if we could do it, which was the recycling of pressure vessels to recover continuous carbon fiber. A bit about our company. We are based in the northwest of England, close to Manchester, 50-year-old company, and we are a specialist machinery builder. We service the composites industry in particular. And you can see here some of the equipment that we build. From left to right on the top, creels for 3D weaving processes, aerospace prepreg machines, filament winding. We're heavily involved in filament winding programs at the moment. What we're most famous for is pan creels, so the pan carbon fiber process, the creels that go at the front end of a carbon fiber production line. Also slitting and spooling, so it's taking prepreg and reducing it into slit tape. And also automation. We have automated packing systems that sit on the end of carbon fiber production lines. There we go. Oh, too far. We also have an innovation center where much of the equipment that we build is available for customers to come and trial their material on our equipment. A try before you buy type of arrangement. And you see on the far right there further description of the sectors that we are involved in. Recycling composites is not new. In the mid to late 90s, a lot of work was going on in the UK, in particular Professor Paul Williams at Leeds University, who was looking into recycling of glass composites, but specifically focusing on the recovery of the polymer, not the fiber. And similarly, at the same sort of time, Dr. Ron Allred at Adherent Technologies in Albuquerque was developing a thermochemical process to recover carbon fiber. Bit closer, yeah. And around the early 2000s, there were obviously quite a few other interests going on, especially in Europe. You can see there that a few universities in Germany were involved, CFK Valistad in Germany, Composite in France, developing different methods. And at the same time, in the UK, a company called Milled Carbon, which became Recycled Carbon, developed the world's first continuous recycling process based on pyrolysis, which eventually became ELG Carbon Limited in the UK. But again, at the same time, the use of supercritical fluids was being explored. In this case, solvents such as ethanol, acetone, methanol, and they're mixed with water at low temperatures and low pressures were being explored. Microwave was being explored in this same period of time by Fibre Advanced Materials in the US. So, why should we recycle? Well, first and foremost, we're all seeing that the projections for the requirement for carbon fiber are growing exponentially at the moment. And imagine that this is the wind blade industry. They want around 140,000 tons of material in the next few years. It takes 2 years to put a carbon fiber line on the ground and get it running properly. So you imagine the problem we have as we go along, and our industry continues to grow, as is being depicted here. There is going to be a shortage. So we have to start thinking about what we can do to bridge that gap. Interestingly, at the same time, we've heard this morning also and yesterday about other methods of recycling. In the University of Nottingham, a fluidized bed system was developed as well. So, and this was specifically used for the shredding, believe it or not, of defense materials, because they have to be shredded before they can leave the site. This mechanism, this system worked very well and helped recover precious metals as well as the carbon fiber itself. The problem is, of course, is that all this that we are producing, and we have been producing for the past 40 years, has to go somewhere at the end of its life. And unfortunately, as the picture on the left will show you, it gets buried usually, which is not a very good thing for the environment. And of course, now we have hydrogen tanks that very soon will become out of service. But the problem is that this material is too valuable to go to waste. So we have to make an effort to do something with it. So, back to my history lesson. So there's great activity in the early 2000s about recycling of carbon fibers. Governments were interested, major companies were interested, and it all stopped. Stock market collapse in 2008, 2009 not only hit the virgin market, but it hit badly on the recycling efforts in the world. And it's taken a long time to come round. Both in the virgin manufacturing industry and also recycling to come back on to the radar. Why? What has changed? Climate change. The rush now is to look into sustainability, to try and treat our planet a lot better than we have been treating it. And even for those, the most skeptical of us in terms of the climate change argument, you only have to look outside the window to realize that something is not correct. Now, everybody's doing it. Everybody has an interest in recycling. Even here in Korea, Katak H and several others, and I'm quite sure I've missed quite a few off here. So there is now this a real push towards sustainability. CFK Valistad, who I mentioned earlier, who were part of Gunnar Hertz's operations in Germany, they eventually turned into a continuous pyrolysis process, but recently they were acquired by Mitsubishi, and they carry on in that collaboration in Germany as a recycler. So to all intents and purposes, we have learned how to recycle carbon fiber. It can be done, both thermoset and thermoplastic. We have been doing it. The most common routes to reuse, though, are only milled, chopped, or non-woven, which are not necessarily the best format to get back into the industry. It has improved. Predominantly, the non-woven is most used because it can be thermoformed. Chopped material tends to go into injection molding, as does milled material. And of course, the chopped material lends itself very well to SMC and BMC. But some of the work we have been doing with some of our partners has been looking again, something you see on the Microsoft stand, that their work that they've done with Catek-H is returning that fibre, that recovered fibre, back into a continuous yarn. In this case with polypropylene, to make then a resin-infused prepreg material, which has then been thermoformed into particular parts. These were for an automobile research and development trial. So it proves that there are routes into reuse, but it's quite a difficult path at the moment, trying to get the virgin users to realize that there is a place for the recycled material as part of their actual manufacturing process, even in terms of a virgin recycled mix. In the UK, the Composites Trade Association asked the composites manufacturers in our country what their next sustainable focus would be over the coming years. And predominantly, it was a case of, first and foremost, waste reduction. But 29% of those that were asked, their focus was on recycling and reuse. So the message is getting out that there is still potential, there is great potential for the reuse of recycled carbon fibre. So we all know the virtuous circle, trying to get this back into the industry has been a tough sell. When I was involved in recycling back in the early 2000s, Boeing and Airbus were the main drivers of interest here as to how they could get this material back into their airplane simply to save weight. But we shouldn't think of it just in terms of recycling. There is the possibility for reuse. Some of these parts that get thrown out or removed from wherever they are still have an element of life in them, and that's something also that we should explore. And also repairing. Repairing a composite part is doable. I've seen the 787 barrel section being repaired quite well. It worked very well, in fact. So it's not simply just about recycling. We've got to think about repair and reuse. And of course, you have seen this from our colleagues at Swancore yesterday, gave a similar sort of chart in terms of the routes to recycling. And these are fairly common now, fairly well known. And there are a number of companies, as I showed before, who use these methods to recover the carbon. But like I said, we have a new olysis, pressolysis. Like all good inventions, this one was found by mistake. This particular system, the decom system, was originally used for cleaning polymer from candle filters. And it was found by mistake that it actually could clean the fibre, the resin, off carbon fibre at the same time. So we, Cygnet texkimp, have secured an exclusive worldwide license to build this equipment from the company, BM Longworth there, also Northern England. And it's quite an easy and simple process. So I'll just take you through that. So our primary concern at this moment in time is, because this is a part of our large R&D activities, is we've got to obviously understand, is it sensible? Does it actually work? Well, we do know it works. The price for this feedstock obviously is of concern in this, to give us an idea of then what our price of the end product might be. Bear in mind, we are not a recycler, we are a machinery builder, but we can advise on the recycling side of things. And of course, the fibre quality, everybody wants to know, are the mechanical properties reduced by the process? And again, this issue of the useful application, what can we make use of it for? So we go through all these stages in terms of evaluating this piece of equipment. In fact, I'm hoping that when I get back to the UK, we will be operational with our new piece of kit. And what we're going to be doing is looking at the basic principles of the system, which is based on temperature, pressure, time, of course, and what we call blowdown frequency. So the decom name comes from decompression. So it's a decompression cycles that remove the resin from the fiber. And so as you know, no two composites are alike. So the unfortunate thing is that there is no one fixed recipe. And so that's what we have lined up in the coming months. We're working with our partners in terms of looking at the different types of materials, characterizing those, and working out a series of recipes for particular types of composites. System itself, it's a 2-meter long pressure chamber, 450 millimeters diameter. It fits a H2 tank very nicely, actually. So it's worked out very well in that respect. It's rated at 585. Well, it's actually rated at 600, but operating temperature is 585, and 15 bar, which is actually way higher than is actually required. But being the research and development guys, they want to play with things and find out what the limits are. It's got a loading bay, sample holder, so again, we can put various types of materials into this. And of course, the idea is monitoring the effect of the parameters. We want to know is strength and modulus affected, because in pyrolysis and such like, tends to affect the strength. And the one thing that we know this process can do is recover the resin. And so we've done some early testing on that, which I can show you some results. So just to take you through it, we have a boiler on the right, the actual vessel in the middle. Will it work? No, I can't see it. So vessel in the middle, and the large vessel on the left is the decompression chamber. So the carbon fiber goes into the pressure vessel itself, the composite waste, the steam system is used, and the polymers collect in the bottom of the large vessel. So the steam, obviously generated by the boiler, 110 degrees C, passed through the superheater. You can see the superheaters there. And from there, the pressure vessel itself, you can see in close-up on the bottom there. And from there, the steam exit and matrix reclamation in the blowdown chamber. So it's a fairly simple process. And all we are emitting to air is water or water vapor, nothing else. So we recover all the resin from the fiber, 99% of the resin from the fiber, and that is collected, and like I say, we've had some material evaluated recently, and I'll show you a slide from that. But we're also looking already, as we are building this, we're looking at ways of reducing the energy consumption that we anticipate in this by recovering some of that heated water back into the system to reduce the energy required, amongst other things. So just a recap on that. Temperatures, it is rated to 600, but we'd only use it at 585. We have thermocouples, pressure sensors all over the place. The vessel itself is rated to 15 bar, but currently we only have a 10 bar boiler on it, but we fully intend to increase that to a 15 bar boiler. And so it produces, the superheated units also have transducers on them. And so we basically, it's bristling with data capture. And what we're looking for, of course, is the energy and cost efficiency based on this. Now, bear in mind, this is a research and development equipment. What we actually build for customers will be nothing like this. It will be much lower spec. Of course, it's going to be fully insulated. In fact, that's ongoing as I speak. And like I say, heat recovery is part and parcel of what we're going to do to it next. So we did a test to see if we could actually do this, which was the recovery of carbon fiber from a hydrogen vessel to see if we could get the long fibers back out of it for reuse. So our first step was to take a known item, in this case a bobbin of T700. We put it through the system and we recovered it on the right-hand side there, and we measured just to see if we saw any degradation of the material at all, both materially and visually. And we found actually there was absolutely no difference to material one to the other after it had been through the process. So you can see on the top there is virgin fiber, on the bottom is some decommed fiber, as we call it. You can see there's still some residual resin on there. We're not entirely sure what that is. That could be size. And of course, size is of great interest as far as recycled material is, because commonly the size is removed completely. But what we found is that we can tailor this to leave elements of the material on there, depending on what the end use is going to be. You'll see here on the side some results which quite frankly flabbergasted me, but these are from Imperial College in London. They did testing for us, and we're basically finding no mechanical degradation at all. So the process that we're going to go through with this is taking it in several steps to see how things work. We've got to work out the length of time and the processing conditions for each type of material that we're going to use. And so it's an iterative process to get down to this final recipe of conditions that we're looking for. So just to take you through this is something we did for the Type 3 cylinder, which was to decom it, to put it in the decom system, remove the resin, collect the fibers, and make another tank. So what you see over there on the right is that tank reconstituted. So we proved basically that we could actually recover the long fibers and reconstitute a tank. Now, it was purely a proof of principle, not for any sort of sensible consideration to remake a hydrogen tank out of that material. That said, who knows? But we also tried Type 5 tank. Now, Type 5 was a bit more of a challenge because, of course, there's nothing inside supporting it. So we did the same sort of thing. We put it into the decom system, recovered the toes, poor souls up there having to suffer that. And one of the interesting things that we found is that obviously we want now to automate this process. And part and parcel of that is that the way cylinders are wound tends to be in courses of 4, usually, although we have seen some variations on that. So the idea here is to recover each toe singly at a time to make sure that we're getting distinct toes. So we're devising like I say, an automated or mechanical system to do away with people having to do the unwinding. And we talked about size. Well, we rigged something up on part of our machinery in the R&D department. And you can see here, this is recovered carbon fiber. being washed, and then size is reapplied. You can't see it's underneath. Then dried, and then collected onto bobbins again for reuse. So again, this issue of size that is still something that's predominantly of concern in the industry. We're looking at the possibilities there of what we can do. So some of the earlier results relative to pyrolysis show basically what we might expect. On the right, you've got the modulus, and even with pyrolysis and our system, the difference in modulus is negligible. But of course, you do see in pyrolysis, you do see a drop-off in strength. You'll see the virgin on the left, then our system, and again, we've gone through several iterations to get comparative results. And you see we're not too far off in terms of the strength there. Those were early days. We anticipate getting much better results as we progress. And I talked about the resin recovery. So the resin that we've recovered from one of the processes was given to Scott Barder, the resin company, and they looked through what the resin constituent parts were and came up and made a resin. The blue resin, if you like, is the original. The blue line is the original, and the red line is that recovered. So again, this was the first time we ever tried this. Again, we have really quite encouraging results in terms of recovery of the resin. So this is something that, like I say, this is an R&D kit at the moment. There is a long list of companies that want to come and play with the equipment to find out what it can do for their material. And what we've also found is that one particular company is very encouraging because they're actually going to give us material, waste material, in a format that we can give it back to them directly, and will go directly back into their manufacturing process. So this idea of building a composite with recycling in mind is really important. Now, it's not always the case that you can do that, but certainly it has to be thought of in that process. So, like I say, when I get back to the UK, I'm hoping this machine will be ready to turn on and commission, and we'll get started. And in due course, of course, we'll be presenting more about what we find. And of course, with all our current partners, we have a few government programs going on that we're involved in terms of the hydrogen side of things. But we're also dealing with the larger aerospace industry as well. And I think that's me. Yes.
Thank you, Mr. Davidson. Is there any question from floor? Yeah, please.
Thank you for your very great presentation, John. Also, I would appreciate for you accept this for my invitation to give a presentation.
And thank you for that.
Yeah,
thank
yes,
you.
we met Seattle. I think I gave a similar the question in Seattle. Would you think about the comparison between the pyrolysis and the solvolysis? And yesterday presented Swanko new methodology. The good point, the better point, which one is optimized?
Well, in terms of pyrolysis, obviously, because it's closer to my heart, I found that because majority of processing systems are batch systems, so it takes time. It's more, and it's less energy efficient actually, but there is room for all of them, and they all have a part to play, and especially what Swanko has done with their recyclable resin, I think is a great thing, because that's going to give us a chance to make our process even more efficient. Because rather than having to battle to get that thermoset or what have you, generally thermoset, off that fibre, anything that makes that easier to do has got to be good for us, because again, if we can do it in shorter time and more efficiently, less energy, less CO2.
And according to you, the slide, you did some resizing again. Also, you showed the carbon fiber surfaces. I can observe the sun remained rigidity 1%, 2%, 3%.
Yeah.
So, in addition to you try to resizing again on the top of the carbon fiber, such a kind of a dirty surface, still okay?
Well, yes, this is the interesting part. A lot of initially, when we started this, people were not so much worried about recovering the carbon or the resin, they just didn't want to have to landfill it. Now, the focus is on capturing both now, the carbon and the resin. But they seem less concerned if there is an element of residue left on the fibre. In fact, certainly in one case, they welcomed it because it gave them a better key to what they were going to do next. So this is interesting in terms of, do you really want fully clean recovered carbon, or do you still want an element of material left on there as part, again, of a key for the next stage, for the next matrix that it may well go into? So yes, it's a mixed interest, really. Some want it as clean as possible so that they can put their own size on it and then onto the matrix. Some are actually interested in having a slight residue left.
What would you suggest for such a practical application like automobile, airplane, UAM, and so on, not including structural application? So what would you suggest for using your recycled carbon fiber particularly?
Well, this is it. It's a case, when I did early work with Boeing and Airbus, they weren't interested in trying to get this back into any sort of structural composite bar. They were interested in getting into the internals of the aircraft, so stow bins, seat backs and things like that, anything that could help reduce the weight. And it is still very much of interest to the likes of Boeing and Airbus. But in terms of putting this sort of material on a car, recycled material on a car, I don't understand why there is not more of it going on.
Even structural applications.
Well, we've seen it on an A-beam of a car where somebody's been playing around with it. Unfortunately, it's a high-end car, which, you know, the ideal situation, of course, is if we could get around 10 kilograms of carbon fibre in mass market cars. Well, frankly, first and foremost, we would never have enough carbon fibre in the world. So this is where recycled carbon fibre has a really good chance of fitting in quite well, because it is a sin to chop virgin carbon, because you don't go to all that trouble to make a continuous tow, put it on a bobbin, and then chop it up. It's nonsensical. So this is where recycled, chopped, non-woven and milled, and in terms of the long fibres, really has a chance to shine in terms of going into automotive and industrial, wind blades as well, to kind of take the pressure off the virgin requirement in these products.
Everybody interested in continuous recycling carbon fiber rather than the short recycling carbon fiber recently. So your methodology can be applicable continuous recycled carbon fiber?
Well, yes, if what, and the problem with waste material, waste composites, it's either manufacturing waste, which is offcuts of pre-preg or shapes of material as they cut it, or it's end-of-life material. So the thing is, it's a matter of how we receive that material, in what form, as to how we can then make use of it. Which is why those three methods of use from the early days was because all we could get was a very mixed up size of materials. So your materials could be 45, 90 degree fabric, or it could be unidirectional. So it's very difficult to actually do something with that other than mill it, chop it, or turn it into a non-woven material. Now, the opportunity, if the hydrogen industry really does kick off and we have tanks coming out of life in due course, if we can recover that as a continuous fibre, then that gives us a greater span of things that we can do with that material. And again, acknowledging that it's recycled material is going to be one of the difficult things for the virgin world, because they seem to think that, oh, recycled, it's lower. Well, so far, that is not the case. Even in the pyrolysis system and the solvolysis system, the material still has a place and can still be used. And this fixation with aerospace grade materials, T700, T800 and onwards, sometimes they get lost in the use. And really, a T300 type material is just as good. And the recycled material, bear in mind that a good deal of it is aerospace material. So it has a lot of work to do yet, but there is a definite place for it in the process of making these composite parts. Okay.
Yeah, let me give some question to you. The recycling is very important, especially now the carbon and nano materials broadly using for not only for aerospaces and sports goods and energies and even the battery cases and electric cars. So if we don't concern about the recycling, then all these carbon materials will be after some life cycle, it will be the pollution.
Yes.
So it's kind of duty we have from commercial side and the industrial side. Yeah. And question is, for example, like a large structure of the wind blade, depends on the parts. They are using not one types of composite because of the spar, the reinforcing the spar, the prepreg, or different thickness, different size, and they are using different sizing agents or different chemicals also.
Yes.
So question is now pyrolysis, even summer method or solvent method, chemical method, how we can make the even quality or reusable quality. I like that you have a slide. Can be reused 2/3. Yes. I don't really little questionable, but reuse 2/3 and repair and recycling. Yeah. So this is very important. Reuse is best things.
Yes.
Repair is questionable how we can repair. But recycling, we have to concern recycling. Then, as you know, last week I was in some ceremony, Toray Korea. They are under construction, new expansion.
Yes.
And Hyosung also new expansion. And I was, last month I was in China during the next 5 years, new expansion only for 80,000 tons. And the final expansion is very big. So already the price of the virgin fiber, industrial fiber, less than $15. And they're expecting like $12, $10. So now we have to concern. We have to do it, recycling. But commercially, if the cost of recycling is higher than virgin carbon fiber, how we can do?
Yeah, well, it's very interesting this, because you've got to bear in mind that there's been this holy grail that we've been after for years in the carbon fiber manufacturing industry, which is $5 a pound for carbon fiber. To my knowledge, we've never got there. The problem is, of course, it's all fossil fuel based. So it's very much tied to price of oil and so on and so forth. And then, so yes, China is expanding massively at this moment in time in terms of production capacity, but so far I don't think there's that much of their materials has appeared internationally yet. They're not quite there in terms of the quality and consistency. So whilst, yes, China intends, without doubt, to challenge all the Western manufacturers as much as possible, they've a way to go yet. But I still can't see the price coming down to that $5 a pound that we talked about many, many years ago, Zolt Rumi. So as far as that difference between the cost of recycled material and the cost of virgin, I still think we're going to have that. There's a good enough margin in that for the recyclers to make a decent living. The problem is getting that material back into a usable format that the people who might be able to use it can use it and use it with some degree of confidence that it meets their requirements. And that takes a long time. I was involved in 2003 in recycling, and one of the hardest things was trying to get people to accept that the recycled material had some value, had some use. And it took me over 5 years. And I must admit, great help from Boeing and Airbus in terms of making people switch on to the idea that actually there is something we can do with this. We lost the march on that because of the financial collapse and the length of time it's taken the industry to get back online again. But it's here again now, and thankfully, because of this need, this sustainability issue that we're all dealing with at this moment, I think that we are going to get greater purchase into the virgin side of things in terms of a mixture of the two, if you like, bringing an element of recycled material back into the virgin manufacturing process as well. Because companies will have to, whether they like it or not. And the biggest problem is, I foresee, is we talk about life cycle analysis. Right now, the only life cycle analysis you're likely to see is for a composite part. That's it. You won't see one for the carbon fibre itself. And that has a massive CO2 footprint. Making polyacrylonitrile from fossil-based fuel, much of which 95% of a polyacrylonitrile is acrylonitrile. Then you've got methyl acrylate, vinyl acrylate, itaconic acid, accelerators, inhibitors, and so on and so forth, all chemical-based. And that goes into making pan fibre, which is in itself is a real energy drain. Then you've got to turn that pan fibre into carbon fibre, and you effectively burn off half of it. So it takes 2 kilograms of pan to make 1 kilogram of carbon fibre. The common, a rough order of magnitude for a carbon fibre line, installed power is 11,000 kilowatts. And that 11,000 kilowatts is switched on pretty much 365 days a year. And it's a very, very energy consumptive process. And of course, as you might imagine, the emissions to air have to be tightly controlled and are tightly controlled. But again, oxidation, the first part of making carbon fibre, can take up to 60 minutes. Some brave souls have got lower with their precursors, that's great. But then you go on to making carbonization. The carbon fibre itself, that takes 3 minutes. But the energy required for that 3 minutes of work is astonishing. You're talking about maybe 2,000 kilowatts. Again, 365 days a year, non-stop. So it's a very, very energy-intensive process. And if we are to pay attention to this idea of sustainability and these so-called LCAs, an LCA for a composite is useless on its own. It has to include the information from the carbon fibre production as well. Otherwise, it's pointless, because all that's happening is that the LCA for a composite part only accounts for when the carbon fibre arrives at their door to when it goes out, and doesn't commonly include recycling either. So we actually, if we're going to talk about LCAs and this force then to make us recycle and consider this, has to include the whole piece. Otherwise, it's pointless. So we have to use the pan manufacturing process, the carbon fibre manufacturing process itself, the process to convert that carbon fibre into a format that then becomes the composite part. And then we have to consider the recycling as well. Because we can't, it's pointless looking at these as individual items or individual steps. It's the whole piece. And the problem is, I don't know how the pan and carbon fibre side of the world is going to reconcile itself to this requirement for a low CO2 footprint. They are trying, there's no two ways about that, but it's very difficult. Carbon fibre production hasn't changed well, I've been in it for 41 years, and it's not changed since I've been in it, and it needs to. But the trouble is, because of the large capital expense of putting these processes in, it's going to be a very slow and painful process, but it has to be done. Otherwise, our industry is going to be stopped. And the idea is if we get in first as an industry and show best practice, this is what we're doing, this is what we're aiming at, and some companies are, with no doubt about that. If we don't do that, governments will prescribe what we have to do. And we all know what happens when governments get involved in industry. It virtually fails. So it's very, very much incumbent on our industry as a whole, not just the composite side of things, but the whole piece from chemistry to recycling. We have to get our act together, or otherwise we could find ourselves out of business.
Thank you. I would like to ask you to continue this developing effort. Two things, very important things. Regardless of this chemical method or thermal method, pyrolysis maybe make a damage of the fiber, or the pyrolysis make some residue. It's not easy to make it perfect separation. So two things. One is performance properties effective. Secondly is cost effectively. So two things we have concern, but please continue develop the
Certainly.
efforts.
Yeah, certainly.
Yeah, let's give him
Thank
a
you.
hand clap.
Thank you.